Hi everyone, and my name is Harsh Bajpayee, and I work at Polygon ID. So, some of you might have heard about it, of you might have not heard about it. It's part of the Polygon ZK initiative. And today, what we are going to talk about is zero knowledge cryptography because there's a lot of buzz around it. And the current problem with ZK as of now is that everyone is hearing about ZK. Everyone wants to get in, but everyone is also confused. Like, I meet people who think ZK is a roll up and not a cryptography. So that's like from where I thought of creating a workshop around ZK, where I could communicate my mental models on how I think about ZK, how my mind is wired towards ZK. What will be the agenda of today's talk? Like, first of all, we will go through an introduction of ZK cryptography, where we will establish that ZK is not only about rollups, it's just a part of what can be implemented through ZK. Secondly, we will go through introduction to zkSNARKs, then to CIRCOM and SNARK.js, which we will come to know what they actually are. And then we will build our first ZK application, and we will do it in 15 minutes, like super quick. And then we will understand few use cases of ZK, and that's where like the roll-up thing that everyone wants to know about will also come up, that how ZK helps implement rollups. So the first question, what is ZK cryptography? What is this thing that everyone is talking about? So it's a way to prove knowledge of information without actually revealing it. And it sounds strange, but yeah, that is what it is. So what does it look like? And let's take a look at a ZK interaction. So in any ZK interaction, you have two parties. First is a prover, and prover has knowledge, like he has information, but they don't want to reveal it because that information is sensitive to them. But on the other hand, there's a verifier who desires the prover to have knowledge, but at the same time, the prover does not want to show them the knowledge, the information. And that is where that is what a ZK interaction would look like then. So the prover has knowledge. They generate a proof of knowledge, which does not contain that piece of information or knowledge in itself. And at the other hand, a verifier can verify that piece of knowledge. But the question is, how is that even possible? How can something like this work? How can I prove that I have a piece of information but not show it? Because that's something that we usually don't see in real life. The way we prove that we have a 100 rupee note is that we show that we have a 100 rupee note. So let's take a small detour. Let's talk about something else that could help understand us this concept better. And that is also like, this is something that I have been working on. I've been creating this mental model to make understanding of ZK cryptography easier. So let's talk about computation. We are all builders. We all know what computation is, right? Computation is basically you take inputs, which is information, you do some processing on them, and then you create an output from them, right? So this is what any basic computation looks like. You have inputs, you do processing on them, and you create outputs. One example could be multiplication of two numbers. You have inputs, x and y, you multiply them, and then you produce an output. And the processing part is a multiplication of those two numbers. The question is, how do we verify computation? Well, we can recalculate, we can recompute, right? So in this scenario, the prover will say, hey, here are the inputs, here is the computation I did, and here are the outputs. And the prover and the verifier will say, okay, let me take the inputs, do the computation again, and verify the output. And that is traditionally how we think of verification of any sort of computation. Hence, redo the calculation or computation, and the verification is done. But the question is, what about heavy computations? What if there's a computation that takes 15 minutes, right? Does it even make sense to spend time 15 minutes each and every time doing that same computation? How can we solve that, right? So what do we do here, right? There has to be a way out, and turns out there is. So what if we could prove correct execution of computation without recomputation? And this might sound bizarre, but let's look at what it is called. It's called verifiable computation. So what verifiable computation is that when you do a computation along with an output, you create a proof of computation. So if you see here, in the blue box, there's another piece of data that is coming out, and that piece of data is called proof of computation. So so basically you can give your inputs, your proof of computation, plus your output to any particular party, and they can verify whether this particular computation was done correctly or not. Interesting. So we can verify any computation just by checking this proof, the inputs, and the output. No need to recalculate. And this concept is called verifiable computation. But interesting question here is that, okay, but how does this relate to proof of knowledge that the quest we started with, right? Okay, so let's look at this. What if you could hide some inputs? And what I mean by here is that, let's look at the old approach. We have inputs, we have proof of computation, we have an output, and at the same time, that's what helps us achieve verification of computation. But what if there was an approach where all we have to provide is just the proof of computation and the output, and we could still verify the computation? You can see it in the new approach row that we have below. So in this approach, something very interesting happens, which is we can hide inputs, which means that we can hide knowledge, right? If you look at it, at this particular computation, z is equal to x into y. There's an output, there's a proof of computation that this computation was executed indeed correctly, and there were two inputs. These two inputs were knowledge, x and y. But at the time of verification, x and y are not required. So in this particular computation, what you are proving is that you know two numbers x and y, which when multiplied results into z. Since you can verify that this was calculated correctly with the proof of computation and the output z, you know the other party had two numbers, which when multiplied results into z. So here you are proving that you know factors of a number, but you are not revealing the factors. So this is how verifiable computation can help us understand how zk cryptography works, like how you can prove knowledge of information to someone without actually putting it. So you just have a calculation, you provide inputs, your pieces of information. The calculation being executed correctly in itself means that you had the input. That's how the calculation is created. That's how the computation is created. So basically, proof of computation plus hidden inputs from proof results into proof of knowledge of inputs. So hello zkSNARKs, because this talk is named SNARK 101. Actually, that is what it is named on GitHub. And let's take a look at zkSNARKs. Like, we have heard this word. Everyone who has been following Polygon zkAVM has heard something about zkSNARK. There are protocols like Mina for using recursive snarks. So what are snarks? Polygon ID uses zkSNARKs. So what are they? Well, they are a zero-knowledge cryptography. So they are a way to achieve zero-knowledge cryptography. And it's a non-interactive form of proof generation and verification, which means that the prover of the knowledge and the verifier of the knowledge, they don't need to interact in real time to prove and verify knowledge of information. So the basic units in a zkSNARK, through which we express this computation that we have been talking about till this far, are called circuits. And these are arithmetic circuits. So for example, if anyone has worked with digital electronics, they remember the NAND gate, the NOR gate. So this is what arithmetic gates are. In this scenario, you can see that A and B are firstly going to an arithmetic circuit, which adds A plus B. And C and B are going to a multiplication gate. And then the computation, and then their outputs are going to another gate labeled as gate 2. So the computation this circuit is expressing is A plus B into C. Of course, A plus B will be evaluated first. Plus, the interesting part here with these circuits in zkSNARKs is that they also generate a proof of computation, that whatever computation was performed through their execution was indeed performed correctly. So, and one question that generally arises in the mind of builders is that, okay, these are primitive gates, right? Like, what will I do with this? In the last example, we had this very simple expression, right? What can I do with it? It looks useless, right? But the thing is that you can combine these gates and create more interesting complex computation. For example, you can create a hasher in which you can put an input, and that input can be any piece of data. It can produce a hash, and it can produce a proof of computation. So the next time, you can just provide the output, which is what the hash is, and the proof of computation, and you don't need to provide the input. Just look at how passwords would look like, how password authentication would look like. The way password authentication as of now works is that someone has stored the hash of your password in their database. Then they send you the password, they hash it again, and they check whether those two passwords are indeed correct or not. But in this particular case, what can happen is that they can send you simply the hash, but they can also send you the proof of computation. They don't need to send the passwords over the internet. So you can simply trust that the other person indeed has the password. And the other component around them is public inputs versus private inputs. So we discussed that we can hide inputs from when we do zk cryptography from the verification process. But there are times when we would want some inputs to be public, that is, some inputs to be required at the time of verification. And what could be a use case where we would require something like that? Yeah, like why would someone even need public inputs? Like why not hide every information in this particular zk implementation? So let's take an example of NFT whitelist. The way NFT whitelist is done is that you have a bunch of addresses. Ideally, you store them in a Merkle tree, but here we will take a simplistic example where you're storing them, let's say, in a vector. And the prover wants to prove that I am part of the NFT whitelist, right? But they don't want to reveal their address. So what they want to simply prove is that out of all of these addresses that are in this NFT whitelist, one address belongs to me. And on the other hand, there's a verifier who wants to verify that whether this person who's making a request is indeed someone who's whitelisted or not, right? So here's what the computation will look like. In the computation, what will happen is you will take two inputs. First will be the list of addresses. Second will be the private key of the person who's trying to prove that they indeed are part of an NFT whitelist. The computation will firstly generate a public key from the private key that has been inputted into the circuit, and then they will check whether that public key is in the list of the NFT whitelist. But at the time of verification, the verifier would also need the list of addresses, because all this computation tells here is that there was a list of addresses, and this person had a private key whose public key is part of that list of addresses. But if the verifier doesn't know what list that is, that doesn't make any sense at the time of verification. So that input can be labeled as public, and at the time of verification, it will be mandatory to provide that particular input so that the verifier can make sure that this list of address is indeed the NFT whitelist that I have made. So here's what the process will look like. The verifier will take the list of addresses that were used at the time of execution of this computation. Then they will take the proof of computation, and then what they will do is that they will check if the list of addresses is correct, which was used to execute this computation. Then they will check the proof of this computation. And if both of these are correct, then it means that this person indeed is part of that NFT whitelist. Yeah, so like my goal here was that I not only talk about this cryptography, but I also end up building something in front of all of you so that we get to know that what it looks like in practice, because there are a lot of talks around it, but a cool workshop around it is something that I've seen is missing. So let's build something around with the mental models that we have gained through this particular workshop. Yeah, so what are we going to build? And we will build an application that we will call zk factors, and it is something that we have already seen in the earlier slides. So basically, we will try to prove that we know the factors of a number through zero knowledge. So this is what a circuit should look like in this case. There will be two inputs, x and y. The computation will be z is equal to x into y. The output will be z, which has to be public, and then there will be a proof of computation. So at the time of verification, we will simply provide this proof of computation, and we will provide the output, and any verifier can verify it. And if this verification succeeds, then the other party knows that we know two number, which when multiplied results into z. So yeah, so that is what the project flow will look like. Firstly, we will write a zk circuit.
Then we will compile that zk circuit. Then we will generate two keys. Now these two keys are called z key and a verification key. So a z key is a key that a prover requires to generate a proof, and a verification key is something that the verifier requires to verify a proof. And the tech stack that we will use here will be SNARKs. It's a language for writing and for writing zk circuits. And SNARKs, it's a JavaScript library that we have written for generating and verifying proof. So both of these projects have been made by the team of Polygon ID. So yeah, let's get started. So to simplify this process of writing the zk application, I spent some time to create my own sort of a framework like Anchor, where you don't have to deal with a lot of complex configuration to start writing your zk circuit. So it is available on Batch Py 244 as zk101. So I will come here. Let's get inside this repo, and let's bring up our Visual Studio Code. So now, just like you have a React, like when you use the create React app, you get this template. This mini sort of a framework that I've created will present you with this particular directory structure, where there are some scripts, and this is what is doing under the hood magic. Okay, yeah, sure. Like the screen is not that clear, so I can definitely understand that. Is it that fine? That's fine. Yeah. So, so these scripts that you're saying is something that I've written to make sure that you don't have to deal with any complexities involved around using SNARKs. So it will be it's as simple as possible for you to write your first zk circuit, and not even first, it can work with any zk circuit. And then you have a folder named as circuit, inside which there's a file which is called circuit.zkSNARKs. So it's, as the name suggests, as the extension suggests, it's a zkSNARKs file, and zkSNARKs is a programming language to write these zk circuits. So here on the first line, we are saying that we are using the version 2.0.0 of zkSNARKs. So there is also a version 1. So we have to specify to the compiler that we are going to use zkSNARKs 2.0.0. Then we have this thing, which is a template. And the question is, what is a template? It's like a blueprint. So if anyone is familiar with object-oriented programming, you can think of them as classes. This is where you specify what your circuit will look like, and you will express your computation here. And then there are components, and components are similar to objects. They are the initialized version of a template. So now moving to our slides, the first thing that we will require here when we look at our circuits is inputs. So these inputs and outputs in zkSNARKs are known as signals. This is getting very near to how digital circuits work, how digital gates work. So the inputs and the outputs here are known as signals. So we have to declare two signals. First is x and y, which are our input, which are the numbers that we will use to execute this computation. So let's get here, and let's declare our first signal. So we say signal, then we say it's an input signal, and then we say we label it as x. Then we declare another signal, and we label it as y, and we declare that it is an input signal. Every signal by default in zkSNARKs is private, which means that they won't be required at the time of verification of these proofs. Now if you go back to our circuit, the last signal that we need is an output signal. And output signals are always public. You can't make them private, because at the time of verification, they are always required. So we'll come here, and we will make another signal, and we will label them as z. Now what happens? So now we will, so yeah, just give me a second. Now what we're doing is that we are assigning z the product of x and y, and at the end we are adding something that we call as a constraint, which will make sure that this computation can only execute if z indeed was the product of x and y. So if z is not the product of x and y, this computation will fail, like it can't proceed. And this is what we call as constraints. So if you create a constraint inside your circuit, and if a successful proof generation happens, then it means that all the constraints you had, all the requirements you had with your signals were indeed met. So in our case, the only thing that we need to make sure once this computation is indeed done is that z indeed was equal to x and y. So now we will install all the node modules that are required. So we'll simply do yarn here, and we have installed all the node modules that are required for working with this project. And if you go back to your presentation, according to the flow, the next process is compiling the circuits. So like as I told that I've created a small framework around it, all you have to do is that you have to write yarn compile, and it has compiled the circuits. So what has happened here, you can see there's a circuit.js folder, there's a wasm file, and this wasm file is basically the compiled output of the circuit. This is what will be executed at the time of proof generation and verification. You see these two files, and you can ignore them for now. And then if we go ahead and we see what is the next process, that is generating the Z key and the verification key. Z key will be required by the prover to prove existence of knowledge. Verification key will be required by the verifier to verify proof of knowledge. So we can come here and write yarn gen key, and it will start producing these keys for us. So there's a process that will go on. It will take around 30 seconds. I could have directly copy pasted the keys here, but I don't want them to somehow magically appear in this template where no one understands where they actually came from. So that's why we will actually go through the generation process. So you're seeing that it is generating a bunch of files, and they will get cleared on, and only the keys will be left after this particular generation is completed. So yeah, we would have to wait for like 10 or 15 more seconds.
Take that as part of the public inputs and say that this proof was verified at this particular time, so that let's say in future someone wants to re-verify, they can also check the public input of time.
Yeah, so basically what you can do in this case is you can create a public input, and that public input can be when this proof was created, and then someone at the time of verification can make sure that whether it meets the timeline that they had decided for which your proof is valid or not. So you can make a public input of time, which will obviously be an integer, but then you can pass the integer in whatever way you want, and then you can at the time of verification verify whether this proof lies in the timeline in which you consider it to be legit or not.
Thank you.
Yeah. Thanks for the question, by the way. We have generated. So here you can see we have a file which is zkey, which is an extension of .zkey, which is what a prover will use to generate proofs. And here we have another file which is a JSON file, and it's a verification key which will be used for verification in this case. So according to the flow, the next process is generating a proof. And generating a proof will require executing the circuit. So we would have to provide the real values of x and y. That's how we deal with real world programs. There are placeholders, we put real world values inside them, and then we execute them. So for that we will create a file which will be called input.json. And here we will specify our input. We will say x is, okay, let's actually take a better example of what x and y should be. So I have this number, and it has 49 factors, and hence it has 1176 combinations. So there could be 1176 factor combination possible for this particular number. So we can take two factors from here. So we can take this particular factor, which can be 1 and 1000, which actually will be the simplest factor we can take. Input.json, we make x as 1, and then we make y as the number itself for which we are trying to prove the factors. We could actually take any other factor as well. Now what we have to do is that we have to generate a proof. So again, as I've made this small framework around it, it's very simple now. You have to say yarn gen proof. And then you have to provide your input file with what inputs you want to execute your circuit, so that you get the proof of computation plus the output. So we provide input.json, and here it is. We have started generating a proof. It's done in 1.34 seconds. Now you can see two files that have been made. One is proof.json. It's a JSON file which is a proof of the computation that we just did. That is, z is equal to x into y. And on the other hand, we have this file which is public.json. It contains all the public data related to this circuit. and the only public data related to this circuit was the output itself. So here you can see this is the output of the multiplication of x and y, and it is in the public data. If we had any input which was public, then that would also come here, and at the time of verification, both the public data plus the proof will be required for verification. So we come here, and at this time we will try to verify this particular piece of proof. So we come and we say yarn verify proof, and then we firstly provide the public data, and then we provide the proof that we have. So what we're trying to prove here is that we know two numbers which when multiplied results into this particular number. And when we press enter, we see, okay, SNARKs says, okay, that's a legit proof. This person knew two numbers, the factors x and y. But what if I try to change this public data? What if I say that, okay, I knew two numbers which when multiplied leads to, let's say 7 for the time being, right? 7. Now when I try to do this, SNARKs will say, no, invalid proof. This is not valid. Like whatever these numbers are through which this computation was executed, they don't result into the multiplication of 7. And isn't that beautiful? Like you are able to verify whether someone had a piece of data without even seeing them. And you know, like this is such a beautiful process. This is what attracted me towards zk and this whole cryptography. So this is not where the story stops. Now I will show you something even cooler. So this is verifying it on our systems, but how about we could also verify these proofs on chain? So basically we could create a verifier in a smart contract, and then we could call that smart contract and verify whether proofs are right or not. So again, we have in this framework I provided this simple command. You can say yarn gen contract, and it will start generating a smart contract for you. So here it is. It has generated a whole smart contract for you, which you can simply copy and paste, and this will work for any circuit that you will ever write. So you can come here, copy it, take it to your remix, paste it here, and then you can deploy it. So we come here, we deploy it, our smart contract has been deployed. And then there's this function which is known as verify proof, which we can use to verify a proof. So let's just do that. For verifying the proof, we will need call data to call this particular smart contract. Again, that is very easy to create. You come here, you say yarn call data. Okay, we would have to check the package.json file. What's the correct command for it? Yeah, yarn gen call data. Yarn gen call data. Oh, the D is small. Thanks. Yes. Yarn gen call data. So here it has produced this random hexadecimal output, and this indeed is all you need to verify proof. So if you see here, the first part before this array, so like here's an array. So this whole part is a proof. It's a zk proof of computation, and inside this array what you have are your public data. So it's your public output. So if you convert this hexadecimal string to a decimal string, you will figure out that this indeed will result into this particular number, whatever y is. So what we have to do simply is we have to copy this data Ninja, and the first thing would be to learn circumlang. This was a very gentle introduction that I provided here, but you should definitely go through the docs. It's a very small language. Then is checking out circumlib. It's a library of these gates that we have made, so you can find a ready-made hasher, and you don't have to write all of these circuits from scratch. We have made a library of all of these circuits that you can reuse. And the last thing is SNARKs. You actually didn't deal with SNARKs directly, because I abstracted each and every use case of SNARKs from here just to make sure that there's this framework available where someone who has no knowledge of zk can just start building applications. So it's somewhat like Anchor, what Anchor does for you. But I would definitely suggest going under the hood, see how I have abstracted all of this implementation away, reading SNARKs and understanding what happens under the hood. It will give you more context. But for now, this template works for you. You can just clone it and start writing any circuit you want. And you can do any kind of proof generation, smart contract generation, verification you want. So now, before we end this talk, I want to talk about some real world use cases of zk, because proving we know factors of two number is not something huge. Like this doesn't sound as something like huge. So number one use case of ZK definitely is scalability, because if we look here, apart from privacy, it is providing us this capability to verify a computation without recomputing it. And this is where your roll-ups come in. So everyone has heard about Polygon zkAVM, everyone has read the tweet, one word zkAVM, and this is what a like a roll-up does. What a roll-up does is that it is doing state transitions, and then it is creating a proof of its transition, that of the state transition from one block to another block, and then that proof is going to the layer 1, as you can see here in this case, and the layer 1 is simply verifying whether whatever state transition happened inside the rollup was legit or not. There's nothing else that the layer 1 needs to do, and that's how you achieve scalability, because you can do off-chain computation and still verify them on layer 1. And the second use case, of course, is privacy. You can prove existence of knowledge without actually sharing it. And one super cool thing that Polygon is building around it is Polygon ID. It's a privacy protecting identity solution powered by zkSNARKs, and I will definitely do an off-stage demo of Polygon ID. So if someone is interested in seeing how it works, I would be more than happy to do that demo. To just give a gist of Polygon ID, in Polygon ID, anyone can issue you claims. You have a wallet, you have your digital identity inside that wallet. Anyone can issue you claims, and then you can prove to other entities through zero knowledge that you indeed own that particular claim. So for example, when someone goes and apply for a job and they have written Harvard in their resume, the way to verify for now is some assistant will call to Harvard and figure out whether this person has actually graduated from Harvard or not, and it's such a tedious process. But with Polygon ID, what will happen is Harvard will issue you a claim that you graduated from Harvard. That claim is stored inside your Polygon ID wallet, physically on your phone, and then someone can simply write. We have a language that we call as claim. Like you can specify any kind of requirement that you have from someone else. So the other party can ask you to prove that you have a claim from Harvard, that you are a graduate from there. And then you can prove that through zero knowledge. You can create a SNARK proof of this particular claim and submit it to them, so the other party can know that, okay, this claim was legit. It came from Harvard. This claim was issued to this particular person who has come to me, and they can simply take you in. They don't have to get in touch with Harvard again. And at any point, if Harvard wants to revoke this claim, they can even revoke that claim, and the proof that you have won't be valid anymore. So this is Polygon ID. So thanks. This was my introduction of zkSNARKs to you, and I hope you liked it, and I hope these mental models help you explore zkSNARKs more in future. So yeah, thank you. Sure.
So basically, there's a WebAssembly file that's been created from the circuit.
Yeah.
So my question is that wouldn't the say the Brave or the Chrome, which is doing this, be aware of the private signal, because we are communicating it from the web application to the circuit? So wouldn't the private signal be known to the browser?
Yeah, if you are thinking that Chrome will steal your private signals, then I don't think, like, yeah, of course Chrome is a browser, so if you do any kind of execution on Chrome, it will definitely know. But I don't think we have to consider Google here, that they would be doing some stuff like that. But you actually don't need to generate these proofs on a browser itself. You can generate them on your local system, because WebAssembly is not something that only runs in the browser. It's compatible with Rust, and you can execute directly on your system. You can generate off-browser proofs as well. But yes, if, let's say, hypothetically, someone makes a browser where they are trying to look at every kind of input that you're doing, then of course they will know your private signals. But we are just assuming that people are good and they won't do stuff like that, because then they will also steal your Facebook password, your Gmail password.
I'm just trying to find loopholes. It's all like I get that.
Oh, got it. No, I thought that you are like concerned about Google stealing.
Second question that I have is the computation that happens on circuits. What kind of computations we can have apart from, like, there are arithmetic computations that you said, but can you just give like what can be done as well in terms of computation, strictly speaking.
Any kind of computation can be expressed here. So arithmetic circuits are very powerful. You can actually combine them to express any kind of computation you want. So you can do hashing. You can work with Merkle trees.
What I meant to ask was, let's say that there is so that there is 1, 2, 3 kind of thing. So like if X does something, then Y does something, then Z does something, like kind of things. Yeah.
Oh, they're not interactive. Like this sort of so you cannot have some sort of internet hook. So you cannot make API calls and stuff like that inside a circuit. It's just normal computation.
Okay, got it.
Yeah.
Any more questions?
Yeah, so you talked about like if Harvard is like giving a claim and they can anytime revoke it. So is it possible to generate a like a system where they are not able to revoke it? Like if we are talking about identity systems like Aadhaar card or something. So in that case, that could like in the wrong hands, it could be a problem.
So actually, I don't see why we would want to implement such a functionality, because let's look at your Aadhaar. Let's say there's you are letting everyone inside some event which has an Aadhaar card, right? But suddenly, Government of India realizes that they have issued an Aadhaar to someone who's actually not a citizen of India and is actually a threat to national security. They need this power to revoke it. So yeah, but if you want to build, you can build it. That's not a problem. That's just an implementation. You can create an implementation where they cannot revoke it.
Okay. All right.
Or as a verifier, you can simply check the claim and not check whether it has been revoked or not.
All right. All right.
Yeah.
Got it.
Any other question, guys? Awesome. Thanks a lot,
Thanks,
Harsh.
yeah.
This was a